Hi everyone. So one of the challenges that we have today is that we don't have physical schools, but still we have to do science. So science without practicals, science without experiments. That's a nightmare. The science would not be existed without practicals, researchers, and experiments. So most of the students requested me to do a video on experimental physics questions because the exams are also coming up. So I decided to do a small video with few questions. Right. We'll try to quickly discuss these questions. Depending on the time, I won't be able to really go into deeply into the question, but I'll try to explain as much as possible. So this question is on momentum, right? As you can see, there are two tracks A and B, and there are two light gates, and the light gates are connected to timers, and all these things are explained here, right? A student has an air track which has two trucks A and B supported by cushion of air. Cushion of air. So why cushion of air? Right, you're right. That is to reduce the friction. Okay, he does an experiment to see whether momentum is conserved. Right. Now when it comes to our experiment, the first thing that we need to know, the expectation, intention. Right, so what's the intention of the student? To find out the conservation of momentum, right? So what are we going to do? Using an air track, reduce friction on the trucks. State why. This is important in a momentum conservation experiment, right? So why it is important to reduce the friction in an experiment where we need to prove the conservation of momentum. Okay. So what is the relationship between friction and conservation of momentum? So we need to see the link first of all, right? Where is the link? Friction and conservation of momentum. Right. So there you have the answer, right? So let's see what's the conservation of momentum. Conservation of momentum is a momentum of a system, closed system is conserved. What do you mean by closed? No external forces acting on the system. So if there's friction, the friction would be an external force. Can the momentum be conserved? No, right? So one of the conditions that we need to have is that there shouldn't be any external force. So that's why we need to avoid the friction. All right. So let's move on to the question part B. The student uses two light gates as shown in the diagram. So there are light gates. A light gauge records the time t taken by the card to pass through it. Explain how would you show that the R track is horizontal before starting the experiment? That's a very important thing. We have to make the air track horizontal, right, before we start the experiment. So why do we need to do that? If the air track is not horizontal, it won't be this much angle, but if it is angle, what will happen is the component of the weight of the glider would be along the air track. So then what will happen? The glider will move on the air track due to the component of the weight, right? So we can't afford to have that. If there shouldn't be any other forces acting here. If there is a force, what would happen? If there is a force, the glider will accelerate, right? But the glider has to have a constant velocity. Otherwise, this experiment will not be accurate, correct, right? So We can't afford to have it. So we need to ensure that the air track is horizontal. So how can we ensure that it is horizontal? There are various methods, right? You can simply use a spirit level, right? So you can keep a spirit level, and the bubble of the spirit level has to be in the center, in the middle. That is a one way of doing it. Okay. What else can we do? What else can we do? Right. So we can simply do this, right? What we can do is, we have two light gates. So we'll use the light gates and the timers, right? So you have a light gate, two light gates, light gate 1 and light gate 2, and they are connected to timers. They are connected to timers. We'll push the cart gently through the first light gate, and then the timer will record the time taken for the cart to pass through the first light gate. When the cart passes the first light gate, once the cart passes the first light gate, the timer will stop, right? And then the cart will come towards the second light gate and passes through the second light gate. And the time taken for the cart to pass the second light gate can also be recorded, right? Now what happens is, when the cart passes through the light gate, the cart crosses the light beam, right? When it blocks the light beam first, the timer starts, and then the cart passes the light beam, the timer stops. So the length of the cart is constant. If the velocity is constant, the time taken for the cart to pass the first light gate should be same as the time taken for the cart to pass the second light gate. So then T1 should be equals to T2, right? So if the time T1 and T2 are equal, we can say that the cart has a constant velocity. If the cart has a constant velocity, that means it doesn't have any acceleration, so no any other forces acting on it. So that means it is balanced. It is balanced as in the air track is horizontal. Okay, right. The next one. See, truck B carries no cart and it's placed so that it's stationary between the light gates. Right. So there is another cart which is cart B. That's stationary. Right. As the cart passes through the first light gate, it records time T1. Right. When the cart A passes the first light gate, it records the time T1. When the truck A then collides with truck B, so the truck A goes and collides on truck B, and after they collide, they stick together and move through the second light gate together, and the time recorded is T2. Both trucks have the same mass. Explain why T2 is equal to 2T1 if the momentum is conserved, right? Now if the momentum is conserved, why the times have this relationship where T2 is equal to 2T1, right? Now if the momentum is conserved, right, we can write an equation considering the conservation of momentum. Momentum before equals momentum after, right? Momentum before collision equals to momentum after collision. Momentum before, what is the momentum before? Cart B was stationary, only cart A was traveling. So let's take the mass of a cart as m and assume the velocity of the cart A is v1 before collision. And then after collision, what happens? after collision, both cards are combined together. So their total mass is 2m. 2m. So obviously their velocities should be now different because the masses are different. So let's assume their common velocity is v2. Right. Now we don't have v1, v2 given. Right. So we have introduced by ourselves. So we have to get rid of them. Instead, if we can introduce time, that will be better. So what we can do is we can introduce time by replacing velocity with displacement divided by time. So what is moving here through the light case? The cards. So the cards has a certain length. Let's take it as L, simple L. So the V1, which is the velocity of the card, can be calculated by dividing the length of the card by the time taken for the card to pass the first light gate. So that is the V1, which is velocity of the card A before it hits the or collides on B, is length of the card divided by the time taken for the card to pass the light gate, that is T1. So the same way, since the same card passes through the second light gate, so the same length, it has the same length, so the time taken is T2. Right. So now ML, all these we have introduced, they can be cancelled, right? So what you are left with 1 over T1 equals to 2 over T2. So you can cross multiply. So you get T2 equals to 2T1. 2T equals to 2T1. So if the momentum is conserved, T2 should be equal to 2T1. Right, good. So the next question. The student records the following data, 5 separate collisions. Right. So when it comes to any experiment, we do repeat the experiment. Why do we repeat the experiment? So that way we can get rid of anomalies, and we can check the validity of our data by repeating, and we can take the average by repeating. We can get the average of the data. But in this case, what we're trying to do is we're trying to basically check the validity of the experiment by repeating it, right? When you do the experiment first, you get T1 as 0.34, T2 as 0.70, and the second time you get different values, right? Accordingly, T2 over T1 ratio is 2.1, 2.3, 1.9, 2 and 2.2. So the ratios are different. Now what's the ratio we initially got between T2 and T1? It was 2. But there is only one instance that we get the same value, 2. Okay. So use this data to discuss whether the momentum can be considered to be conserved in this experiment. Now if the momentum is conserved, we know that T2 over T1 should be 2. Right? We already proved it. So how do we deal with this set of data just to prove that the momentum is conserved? What are we going to do with all these set of data? We can check the uncertainty of these data. How uncertain? So what is the range and the percentage uncertainty of these data? So what we can do is, first of all, we can find the average of T2 over T1. T2 over T1 ratio. How to find that? First, we need to check whether there are anomalous points. No anomalies, because most of the values are close. So we'll consider all the values: 2.1, 2.3, 1.9, 2.0, 2.2. All are given in seconds. No, there's a ratio. This is a ratio. Divided by how many values? 1, 2, 3, 4, 5. So what do we get with this? We get 2.1. That's the mean. We get 2.1. That is the mean. So then, how are we going to find the uncertainty? So we need the range also, because percentage uncertainty is range over 2 divided by the average. So we need the range. How do we find the range? Range equals to maximum minus minimum. So what is the maximum value? 2.3. Minimum is 1.9. That's the range. So then what is going to be the range? 2.3 minus 1.9. It's 0.4. Right. So the uncertainty, absolute uncertainty is range divided by 2. 0.4 divided by 2, which is 0.2. That is the uncertainty. So let's find the percentage uncertainty now. Percentage uncertainty is range over 2 divided by the average. That is uncertainty divided by the average, and into 100%. That is 0.2 divided by average is 2.1 into 100%. So how much do we get? .2 divided by 2.1 into 100%. Is is 9.5. Right. So this is the uncertainty. This is the uncertainty. Right. Now what else we need to do? So we found the uncertainty. Now what is our expected value? 2. Then what are we going to do? We are going to find the difference using the expected value and the given value. Right? How do you find the difference? How do you find the difference? So difference is the expected value minus the value that we have calculated, which is going to be, directly take the percentage difference. Percentage difference is the difference between our value, which is 2.1, and and the expected value versus the expected value into 100%. Okay. So what do we get? 2.1. 2.1 minus 2 over 2 into 100. So we get 5%. Right. So our percentage uncertainty according to the expression 9.1, and the difference, percentage difference is 5%. So the percentage difference is less than the percentage uncertainty. So that means this is valid. The experiment is valid. So the momentum is conserved.